Right, let's do this. Today, we're taking a deep dive into fusion power. We've got this super interesting article from source name. It just came out on February 28th, 2025.
Yeah.
And honestly, it got me thinking about fusion in a whole new way.
Yeah, what really jumped out at me was how it focuses on what happens after you actually get a fusion reaction going. I mean, everyone's so focused on making it happen, which is obviously like a massive challenge in itself. But this article is all about what comes next, once the plasma is actually burning.
It's kind of like, okay, you've built your mini star on Earth, so what now?
Right.
And that's what this article digs into, this whole what now.
Yeah.
It talks about all this stuff like radioactive buildup, fuel efficiency, and wait for it, carbon.
Carbon.
Yeah, crazy, right? Carbon.
Yeah.
It's not exactly the first thing you think of when you're talking about, like, these cutting-edge fusion reactors.
No, not really. Turns out, though, carbon can be a real pain in the neck when it comes to fusion. But before we get into that, maybe we should make sure we're all on the same page about, the fusion basics. So imagine trying to recreate what's happening at the center of the sun, where hydrogen atoms are fusing together to make helium and releasing a crazy amount of energy in the process.
Right, fusion in a nutshell. And one of the main ways they're trying to do this is with something called a tokamak. Actually, we've talked about ITER before on the show, the International Thermonuclear Experimental Reactor, which is basically a giant tokamak, and they're trying to prove that fusion power can really work as an energy source.
Exactly. And to get a sustainable reaction, we need to understand how that superheated plasma, which is basically the fuel for the fusion reaction, interacts with the walls of the reactor. Now, this isn't just about keeping things neat and tidy, it's about preventing contamination and keeping the reactor itself from, falling apart.
Got it. So the plasma needs to stay hot and pure for the reaction to keep going. But how does this all connect back to this carbon mystery?
Well, the article dives into some experiments that were done at the DIID tokamak, which, you might know, uses graphite walls right now. And graphite, of course, is a form of carbon. The scientists were originally looking at how deuterium, which is one of the main fuels in fusion experiments, interacts with boron coatings. They use these coatings to try and reduce impurities in the plasma.
So they're looking at boron to keep the plasma clean. And they're doing these experiments in a reactor with carbon walls. What could possibly go wrong?
You got it. It turns out that even tiny amounts of carbon can mess things up by trapping the deuterium fuel. The carbon and deuterium, they form this bond that's so strong it takes crazy high temperatures to break them apart, and that makes it super hard to get rid of that trapped fuel without damaging the reactor walls.
Hold on, you're saying the fuel gets stuck to the walls? Yeah. How big of a deal is this? Is it like a little bit of residue, or are we talking about a serious amount of fuel being lost here?
It's a pretty big deal, especially if we're thinking about, fusion power on a commercial scale. Think of it this way. You need a constant supply of fuel to keep that fusion reaction running. If a lot of your fuel keeps getting stuck to the walls, it throws everything off. It makes the whole process less efficient, and it could even force them to shut the whole thing down.
Yikes. That sounds like a major headache. It also makes me wonder, why are they using graphite walls in the first place if carbon is such a problem?
That's a good question. And it kind of shows how fusion technology has evolved over time. You see, graphite has been a popular choice because it can handle those insane temperatures inside the reactor. But as we're learning now, it comes with this big downside of carbon contamination. That's why future reactors like ITER are designed to use tungsten walls. Tungsten is way less likely to have this issue.
So it's like a material science problem. Find something that can handle the heat and won't eat up all the fuel.
Exactly, and that's just one part of the whole puzzle. We also have to think about what this means for tritium, which is another key fuel in fusion reactions. Now, those DID experiments focused on deuterium, but tritium is radioactive, right? And there are strict limits on how much tritium can be in a reactor at any given time.
Right, you mentioned that before. Too much tritium and the whole thing shuts down. So how does carbon contamination play into all of this?
Well, picture this. You've got your reactor going, and deuterium is getting stuck to the carbon in the walls. Now, some of that deuterium might fuse with other deuterium atoms, and guess what that creates? Tritium.
Ah, I see what you're getting at. If the deuterium is stuck to the walls, then the tritium it makes could get trapped there too, and that could push the levels over the safety limit.
Exactly. It's like a chain reaction. And it brings up another layer of complexity.
Yeah.
All the regulations surrounding fusion power. If carbon contamination leads to too much tritium building up, it could set off a whole wave of safety concerns and regulatory hurdles.
Yeah, so it's not just like a scientific problem. It's a whole regulatory mess too, right? This article from the Princeton Plasma Physics Laboratory. They call it PPPL. It's like a wake-up call, you know? It makes you wonder how this whole carbon thing might affect these big projects like ITER, which are already facing like a ton of technical and financial challenges as it is.
Oh, yeah, absolutely. That's a really important point. I mean, ITER is supposed to show that fusion power can actually work on a large scale, right?
Yeah.
Like pave the way for commercial reactors. But if this carbon contamination thing causes all these unexpected problems with tritium buildup and then, like you said, all the regulatory stuff, it could really mess with the project's timeline and budget.
And we can't just like magic the carbon away, right? The article says that even though ITER is going to use tungsten walls, they're still expecting some level of carbon contamination. So what can they do? Are we just stuck with this carbon problem?
Well, researchers are definitely not giving up that easily. They're looking at a bunch of different things they could do. One idea is to develop new materials that are even better at resisting carbon contamination than tungsten.
Like a super tungsten, what would that even be like?
Think about materials with like these crazy complex structures, like engineered at the atomic level to actually repel carbon. This is where like nanotechnology and materials science come in. It's a really cutting edge field that could like completely change not just fusion, but tons of other industries too.
That's wild. But developing new materials takes a long time, doesn't it? Like years, maybe even decades. Wouldn't that just delay everything even more?
It could, yeah. That's why they're working on other solutions at the same time. For example, they're looking into more advanced cleaning techniques that could get rid of that trapped carbon and fuel from the reactor walls.
So like a super-powered vacuum cleaner for fusion reactors.
I know.
One. But seriously, how would that even work? Are we talking about like robots going in there and scrubbing the walls?
Haha. No, it's not quite that simple. Some of these techniques use things like lasers or plasmas to basically blast away the impurities, and others use chemical processes to like break down those carbon bonds. It's a really complicated field that's still developing, but they're getting some interesting results.
Okay, so we've got new materials in the works and these high-tech cleaning methods. What else are they thinking about?
Well, some scientists are thinking even bigger. Like, what if we could design reactors that don't have that much carbon contamination in the first place? Or even none at all?
That's really thinking outside the box. Are you talking about totally different reactor designs?
Exactly. There are other designs out there, like stellarators and inertial confinement fusion. They have different setups that might not have this carbon problem as much.
So there are all these different solutions they're exploring. New materials, cleaning techniques, and even totally new reactor designs.
Yeah.
But how do they decide which way to go? What are the main things they're thinking about when they make these decisions?
Well, it's a complicated decision, and there's not really an easy answer. Cost is a big factor, of course. Developing new materials and technologies is expensive, and they need to find solutions that actually work and aren't too expensive.
Right. Fusion power has to be affordable if people are going to use it instead of other energy sources. What else are they considering?
Time is another big one. They need solutions that can be put in place relatively quickly if we want to see fusion power become a reality, like in our lifetime.
So it's this balance between finding the best solution and getting it out there as soon as possible. What about safety? That has to be super important, right?
Absolutely. Safety is the top priority. Any solution has to meet the highest safety standards. I mean, remember, we're talking about a really powerful energy source here, and what people think about it is going to play a huge role in whether or not fusion power is actually adopted.
It makes you think about the bigger picture, doesn't it? We've got this global energy crisis going on, and climate change is a huge threat. Fusion could be a game changer, a clean and almost unlimited source of energy. But what happens if all these challenges with carbon and tritium delay fusion power by decades? What does that mean for the planet?
It definitely shows how urgent this research is. The stakes are high. Finding solutions to these challenges, even though they seem small, could have a massive impact on the future of our world.
This whole carbon thing really shows you something interesting about science, don't you think?
Yeah.
It's not always a straight line to progress. Sometimes you hit these unexpected roadblocks, and you have to rethink everything and come up with even more creative solutions.
Yeah, it really makes you think, like, what other surprises are waiting for us out there? Are there other, like, little things that could end up having a huge impact on, the search for clean energy? Oh, I'm sure there are. I wouldn't be surprised at all. It's often those, like, unexpected challenges that lead to the biggest breakthroughs, And when you think about how complicated a fusion reactor is, it's almost a given that we're going to run into more problems along the way.
Right. Thinking back to that whole carbon thing, it really shows how important it is to understand every single detail of a fusion reaction. Even the tiniest things can have these ripple effects through the whole system.
That's exactly it. It reminds us that we have to look at fusion research as a whole, you know? It's not just about getting the reaction to happen. It's about understanding and managing all the complexities that come with it.
Yeah. So we've talked about the carbon problem, the solutions they're working on, and the bigger picture for fusion development. What do you think is like the most important takeaway from all of this?
I think the biggest thing is realizing that fusion power isn't like a single problem to solve. It's more like a whole bunch of interconnected hurdles. We can't just focus on one thing at a time. We have to think about how everything connects, you know? Material science, plasma physics, engineering, regulations, even what people think about it.
Like this multidimensional puzzle.
Yeah.
And each piece affects all the others.
Yeah.
And the carbon issue, like we've been talking about, is just one piece of that puzzle.
Yeah, exactly. And as we learn more about fusion, we're probably going to find even more pieces. Some of them will fit right in, and some of them will, you know, throw a wrench in our plans.
That leads to a question for you to think about as we wrap up this deep dive into the world of fusion. If carbon is the villain here, what are some innovative solutions scientists could explore to, like, minimize or even get rid of its impact on fusion reactors?
That's a great question. And it's a tough one. Maybe we need to look at entirely new materials engineered at the atomic level that, like, completely ignore carbon. Or maybe we need to redesign reactors from the ground up to come up with systems that just don't allow carbon to build up in the first place?
Those are some pretty big ideas. Maybe the answer is a combination of different approaches. Like maybe it's about improving existing materials like tungsten and coming up with better cleaning techniques and exploring those alternative reactor designs all at the same time.
Yeah, that's what's so cool about science. There's rarely just one answer. And the best approach often involves doing a lot of different things at once.
And it's exciting to think about all the breakthroughs that might come from this research. Who knows, maybe we'll discover some totally new materials with properties we haven't even thought of yet.
The possibilities are really endless. And as we keep pushing the boundaries of science and engineering, I have no doubt that we'll come up with innovative solutions to the challenges we're facing.
Well, I'm definitely feeling inspired after this deep dive. Thanks for joining me on this journey into the world of fusion, where even carbon can become, like, an unexpected enemy.
My pleasure. And remember, this quest for fusion energy is proof of how creative humans can be. And it shows how committed we are to creating a better future.
That's it for this deep dive. We'll catch you next time for another exciting exploration of the world of science and technology.